So this is an angled launch problem. When you get to be seniors, you'll be given the launch velocity and you'll be given an angle, and then you'll essentially be breaking it down into horizontal and vertical like you see here. But immediately, your instincts for projectiles are such that you should be looking at these two numbers, the 25 meters per second and the 40 meters per second. You should be thinking, is that a horizontal thing or a vertical thing? Okay? It says it very explicitly here, horizontal and vertical. But we're going to be taking those numbers and thinking of them as horizontal and vertical. First thing you want to do is draw a diagram. This diagram, even though it may not be automatically obvious how it's useful or not, it's going to help us understand what's happening in this projectile. It's going to help us solve this problem. Also on your test Wednesday, I will probably ask you in some form or another to draw an angled launch diagram, which is different from a horizontal launch diagram, which we've drawn many times. The key to an angled launch is you want to just assume that there's a ground level and that it's going to come back to the ground level. And planning ahead, I'm going to go back and look again really quick. My vertical velocity was 4. So how many dots do you think I want to draw here? Because we always draw the dots first. How many dots do you think I want to draw? It's kind of a tricky question. Very tricky question. There's 8, kind of, but there are not 8 dots. There are 8 intervals. So you need 9 dots. So we're going to draw 9 dots total. Okay? What's that? So I'm gonna move over. I'm gonna move over a certain amount horizontally, but then when I place this dot, it's the biggest vertical gain. So this vertical gain is going to be the most of any dot, and this horizontal gain is going to be constant. So I'm drawing 5 dots up to the peak. Seems about right to me. And what I'm doing here is I'm just trying to make it gain less and less vertical height, but gain the same amount of horizontal distance as we go. If you look at that, roughly speaking, because this is a sketch, I think you can see the key is that the horizontal spacing from here to here, these are not velocities, I'm just showing the spacing from here to here, from here to here, from here to here. Those are not velocities, those are horizontal displacements, but I think you can see that they're roughly equal throughout. And the vertical spacing, it gains the most in the beginning, then it gains less, and then it gains less, and then it gains less vertically and horizontally. Again, it's a sketch, it does not have to be perfect. Now I'm going to mirror this on the other side. That's actually not a trivial point about projectiles. The fact that it does the same thing going down is what's going to allow us to solve this problem. And my line's not nice and straight, so that last point's not as close to the ground as I'd like, but I think you get the idea. Now I'm going to draw all of my velocity vectors in, and I'm going to draw my horizontal velocity going like this. This is not necessarily going to be to scale. I'm not as worried about whether like the 25 and the 40. Now I need to make all of my horizontal velocities the same. And you can see that as the ability to draw this diagram accurately represents a lot of projectile knowledge. Already, we have to understand free fall acceleration and the lack of acceleration in the horizontal direction. So it's not perfect, but those are all basically the same. I'm going to draw my greatest velocity in the beginning. There's going to be less velocity at the next point, less velocity, and the minimum velocity. Now all the corresponding velocities are the same as their counterpart on the other side, but they're going down. I think you can see a symmetry. You'll notice that the second half, this should look familiar. The second half is just the horizontal projectile launch diagram that we've drawn many, many, many times. Okay, so what we're going to focus on here is for the various questions, we can start labeling things. And I'm going to solve part A using just this portion. Okay, using just that portion for part A. So let me redraw that right here and larger. And I believe part A just asks, what is the launch speed? Is that correct?
Yes.
Okay. So I'm going to label these. This is 25 meters per second. It's good to put the units in so that you don't mix it up. Is that a height or a range? No. Some people think this is a range because it's horizontal. No, it's not. The range is this distance from here to here. That's the horizontal range. Some people think this is a height. It is not a height. It is the initial vertical launch velocity. Okay, so I'm simply going to redraw this tip to tail. I'm going to draw my resultant vector, r, and use Pythagorean theorem, 25 and 40. So it's just Pythagorean theorem with those two quantities. I think that's like 625 plus 1600, but please confirm that on your calculators for me. And let me know if I'm making any silly math mistakes. I'm not going to try to square root that, but my resultant, which represents my launch speed, is
47.2.
So I've now successfully solved part A. This was the solution to part A. Now to solve part B. And the great thing about watching a YouTube video, I mean, if the video is going too fast, you just pause it, you rewind it, you watch it over and over again until it makes sense to you. Now, I'm going to use a little bit of logic here. And that's what I encourage you to do. Not so much to do this as an equation, but look at the logic. This is going to be 40 meters per second. And this is when I said it takes a little forethought. I did this by design. This is 30 meters per second. You can see where we're going with this. 20 meters per second, 10 meters per second. This again is going to be 10. It's going to be 20, 30, and finally 40. You can see the symmetry in there. And these were at 1 second intervals. These were 1 second apart. So don't count the dots, count the intervals. Okay, count the intervals. So 1 second intervals, and if you simply look at the number of intervals, 1, 2, 3, 4, 5, 6, 7, 8 intervals. There are 8 1 second intervals, so I believe it was B, 8 seconds. And a lot of you will just develop a shorthand where you realize it's going to take 4 seconds to get to this top, where vertically the v sub y is 0 at the top. A lot of you are going to realize that. Now for part C, if we're looking at the horizontal because it wants to know the range, we want to find d because d is the range. My velocity horizontally is 25 meters per second. And the only equation you ever use in the horizontal, and I'm writing it as dx equals vxt, you can think of it as d equals v average times time. It's just distance equals rate times time because it's constant velocity. So the d is just equal to the 25 meters per second times the total amount of time that it's spent. And if you have 8 quarters, how much money do you have? You have $2. So that's 200 cents. In this case, it's not cents, it's meters. That is the horizontal range that this thing covered. And can anybody tell me, so this was this is what we just solved for, that's 200 meters. And can anybody tell me how you'd figure out the height? Chandler?
You can plug it into 1/2 GT squared.
Very good. What would you plug in for the time? If you want to get d, what would you plug in for the time? Sabrina?
4.
You'd plug in the 4 seconds, because if you wanted to get the height, maybe that'll be a bonus on the test or something, but if you wanted to get that height, you'd want to look at just the second half of the motion where it falls that particular height. So to summarize really quickly, the diagram was enormously useful to solving this problem. You wouldn't have to use it, but the diagram shows that this thing, first of all, had a speed in the very beginning that was just the vector sum of those two velocities. It had a time in the air that was based mostly on that 40 meters per second, because that 40 meters per second tells you how long it takes to get down to 0 seconds here at the peak. 4 seconds, and then two intervals of 4 seconds. And then finally, to get the range, you just take the time and multiply the time of 8 seconds, and you multiply it by the horizontal velocity, because the horizontal velocity is constant.